Hey guys, this is the introduction video for Math 85, Module 6, the last module of the course. So, Module 6 deals with quadratics, and we've seen quadratics before. I think it was in Module 2, where we had a quadratic expression, and you know what, we could even make it a quadratic equation. And we could solve the quadratic equation by factoring. And what factoring did was it created linear factors, and then we could set each one of those factors equal to 0, and because each factor is linear, they're pretty easy to solve. In the first one, we could just subtract 4 on both sides and get the first solution to be -4. And here we could add 2 to both sides and get the second solution to be 2. And those solutions were pretty easy because our factors were linear. But unfortunately, all quadratics don't factor. For instance, the one we just got done factoring was really nice because in general the quadratics look like this. Some number we call a times x squared plus bx, where b is an actual constant number, plus c. That's a quadratic where a, b, and c are the numbers in front of x squared, x, and the constant respectively. And to solve, we have to set these equal to 0, and our first example factored really nice. But what if a, b, and c didn't have the properties that allowed us to factor? Well, then we have to do something else. And in this module, you'll see that if you have a quadratic that doesn't have that middle bx term, like in this case, let's say that we have this quadratic that says x squared minus 9 is equal to 0. There is no middle term that's this bx term. Well, if that's the case, then what we could do is we could just move the c term over, that constant over, and then do the opposite operation of a square. Remember, the opposite operation of a square is the square root. But whenever we take the square root of a constant, we have to include the square and the square root cancel. We have to include the positive and the negative values of that square root. In this case, it's going to be a positive 3 and a negative 3. But what if you do have that middle b term? Then what happens? Like in this case, this quadratic will not factor, and it has this middle term here. So we can't use that square root property that we saw before. So what we do is we use a technique called completing the square. And what that does is it forces us to have this perfect square that we don't have, because if we have a perfect square, like we did here, that equaled, I'll get it here in a second. If we have this perfect square that equals some constant, then we're in business. So we have to create that perfect square, and here's how we do it. First of all, you need to make sure that the a value is an understood 1. In this case, it's understood to be 1, so we're good to go. If there's anything other than a 1, then we would divide everything by that number so that x squared will have an understood 1 in front of it. But we're good to go. The next thing you do is you move the c term over. The c term, in this case, is minus 9, so we move it over by adding 9. And then we have to put in a replacement for this value that we moved over. We have to replace the c term. And we have to be kind of strategic about this. So what goes into this slot is going to be found by taking half of the value of b. Remember, this is the b value. Take half of b and then square it. Well, let's do that over here, maybe in a little thought bubble. Half of b, so b is 4. Half of 4 is 2. And we can square that, and we get 4. So that's the value that we're going to add in there. And if we add it to one side, we have to add it to the other side. So let's see what we got. We got x squared plus 4x plus 4 equals 9 plus 4, and we can, I'll just erase that. 9 plus 4 is 13. We can actually put 13 there. That was just 9 plus 4. And now, look what happens. This quadratic does factor now. We can factor it into x plus 2, x plus 2 equals 13. Hey, you know what that is? X plus 2 times x plus 2 is x plus 2 squared. There's the square that we want, and that's perfect because now in the next slide we're going to come over and take care of that square. We want to take care of that square so that we can create something that's linear. How do you undo a square? Square root. I was a little bit, I was jumping the gun a little bit there. Square root that 13. Whenever we square root a constant like 13, we got to include the positive and the negative version of that number. So let's see what happens. The square root and the square cancel. We're left with x plus 2 equals the positive and negative versions of the square root of 13. And now, perfect, that's linear. All we have to do is just subtract 2 on both sides. Now when we subtract 2, we can't subtract it to that square root because they're not like terms. So the x value is the positive and negative version of the square root of 13. That does not reduce. You could factor tree and check it, but it doesn't. Minus 2. I guess another way you could write it is minus 2 plus a minus square root of 13. What this really means is it really means that we have one value that comes from minus 2 plus the square root of 13. That's all we can do there unless we get a decimal approximation, and I'm not going to do that here, but we could. Or the other solution might be minus 2, not plus square root of 13, but minus square root of 13. And that would give you another value. That's what this plus and minus means. It means that you do two separate things. You add and you subtract that square root. So I think the last thing that you're going to be doing in Module 6 is you're going to be taking a quadratic, but now you're going to be dealing with a quadratic function, which is indicated by that y equals. And the quadratic function is not going to be linear. It's not going to be a straight line, but rather it's going to be this thing called a parabola. And the graph of the quadratic called the parabola will look like a U, or maybe it might even look like an upside down U. But one of the key characteristics of this graph is that this graph has a minimum point, the point at which it bottoms out, or a maximum point, the point at which it tops out. A very important point, because a lot of times we want to talk about maximizing and minimizing, like you want to minimize risk and you want to maximize profit. Well, a lot of times this idea of maximizing or minimizing is indicated by a quadratic. This maximum point and minimum point is called the vertex. So in this module you'll learn how to find the vertex. And that vertex will be the key to graphing this parabola, because the graphs are symmetric right down the middle of that vertex. You can see that it reflects the same distance across the line that goes through the vertex. It shows symmetry, so that vertex can help you graph the quadratic, which is called the parabola. Okay, well, I just want to remind you that you have an application activity that has to be written out and turned in for your final application activity project, so be sure to hand that in, and then you'll be done with the course. So congratulations and nice work.